Hey guys, welcome to Physics 390, class 22. In this class, we're going to be talking about the Wkb approximation. It's an approximation which can be used to get an estimate of the wave function. And it's often used for to get estimates of bound states and of tunneling, as we'll see. And this comes from chapters 9.1 to 9.3 of our textbook. All right, so let's check this out. So the basic idea and form of the Wkb approximation. So first, as I said, the Wkb approximation is a technique for finding approximate solutions to the time-independent Schrodinger equation in one dimension. And it's often used to find bound state energies and quantum tunneling rates. So let's take an observation. If v of x is constant at v naught, then the wave function has a constant amplitude, okay? So if the energy is greater than v, or v naught rather, this should be v naught, then we get a traveling wave solution, which is a complex exponential solution, a e to the plus or minus I kx, where k is related to e and v naught in the usual way. If e is less than v naught, then psi will be equal to, you get a decaying exponential, and psi is equal to a e to the plus or minus kappa x, where again, kappa is related to e and v naught. But the important thing is that if v of x is constant at v naught, these coefficients a and this k and this kappa have a single value, okay? So suppose that v of x is not constant at v naught, but it varies slowly in space, okay, as compared to say 1 over k, because remember k has units of 1 over distance. So 1 over k is a distance, or 1 over kappa, because kappa is a 1 over distance. So if it varies slowly in space, then the wave function should take a similar form to what we would get with v of x constant, but with the amplitude a and the variable k or kappa, that is what appears in this exponent, now becoming slowly varying functions of x, because v of x is not constant, but it varies slowly. So over some interval, it will appear to be constant. So it has the same form. It's just that the a becomes, as we can see here, psi of x becomes a as a function of x, and e to the I now phi of x, okay, where phi of x is taking the place of either kx or kappa x, okay? So this is the basic assumption of the Wkb approximation, that v of x is not constant, but varies slowly. Okay, so let's look at a couple of cases. The first is the case where E is greater than v of x. And this is the classically allowed region, where the total energy is greater than the potential. So there's energy left over for there to be kinetic energy and for the particle to move. So this is an allowed, classically allowed region. So if E is greater than v of x, the classical momentum, P of x, will be, because the kinetic energy is p squared over 2m, you can solve for the P using the relationship that the total energy is the kinetic energy plus the potential. If you solve for P, you get square root of 2m times E minus v of x. And if E is greater than v of x, then this quantity will be real, because E minus v of x will be positive. The square root of a positive number is a real number. So this is real. And then after inserting our Wkb assumption, psi of x is a of x e to the I phi of x into the TISE, doing some algebra and making one approximation, okay, based on the fact that a of x varies slowly with x. And you can check the text for this. It has to do with ignoring the second derivative of a with respect to x, because it's varying so slowly that the second derivative can be ignored. Anyhow, we find the following expression for the wave function after some, I say it's some algebra and an approximation. So psi of x turns out to be a constant over the square root of the classical momentum times e to the plus or minus I over h bar integral of p of x dx. Okay, so the antiderivative of p of x dx. Okay, so that's a nice expression. It's very general because we can say this v of x varies in space. It tells us exactly, it's a closed form expression for exactly this, the wave function in terms of v of x. And if this integral here, we can often do this numerically if v of x is an irregular function. But anyhow, to get some insight into this, we can look at the probability density, which is psi x squared. And that's approximately equal to, well, square this, take the complex conjugate of this times itself, we get c squared over p of x. And then this e to the I will, when we take the modulus squared, will cancel itself out. So we just get c squared over p of x. And this makes sense in that if you think about it, so this is saying the probability density is inversely proportional to the momentum. So the particle spends less time where its momentum is greatest. So if it's moving fastest and it has the highest momentum at a given position x, it makes sense that its density is smallest at that position. Okay, so that's one application of the Wkb approximation. The second one is for E less than V of x. This is the classically forbidden region, because with the total energy less than V of x, there's no chance for we would have a negative kinetic energy, which is not possible. So this is a region where the particle couldn't go classically. So if E is less than V of x, then the classical momentum expression, P of x, again, the same expression we looked at in the previous slide, is going to be imaginary because E is less than V of x. So E minus V of x is negative, and the square root of a negative is imaginary. Okay, so we find in this case a similar solution, again, using, plugging this, the form of the WKB form into the TISE, doing some algebra, providing some approximations. So it's a similar form to what we found before for the E greater than V of x case. It's approximately equal to C over the square root of the modulus of P of x, since we need the modulus because P is imaginary. So we can't just divide by an imaginary number. We need to take the modulus here. And this is plus or minus now 1 over h bar, the integral of the modulus of P of x dx. Okay. So this becomes a instead of a oscillatory function, this becomes a decaying exponential function because there's no I here to make it oscillatory. It's just plus or minus some function of x, which makes it a decaying or growing exponential. Okay, so how could we apply this? Well, suppose we had a kind of a rectangular barrier with a bumpy top. So here's a barrier. We have a bumpy top to it. So this would be really hard to solve normally with the Schrodinger equation because it's an irregular function. But the Wkb approximation gives us a way to work with it. So it turns out that so we have an incoming wave from the left with amplitude A, that'd be e to the I kx, an outgoing wave b e to the minus I kx, and then over here a wave going to the right f e to the I kx. So we have an incoming, a reflected, and a transmitted wave. In between 0 and a, for 0 less than x and a, our energy is less than v of x. okay, because we're below, we're over that whole range, the energy is below the potential V of x. So therefore, our wave function will be the sum of these two forms here, one with C with the positive sign, and one with D with the negative sign. Okay, so this is just this form here, one with C with the positive sign, and one with a different coefficient D with the negative sign, because each of these plus or minus are valid solutions. So the general solution would have both. Okay, so it turns out that you can make some arguments with some work and matching boundary conditions like we always do in scattering problems. And with some reasonable assumptions, we can arrive at a ratio of the transmitted amplitude F to the incoming amplitude A. Okay, so F over A turns out by matching the boundary conditions with this solution inside between 0 and A, and matching everything up and solving for the ratio of F over A, or the magnitude of F over the magnitude of A, turns out to be e to the minus I over h bar, integral from 0 to A, so integral over this range of the absolute value of P of x prime dx prime. And it's absolute value because this is an imaginary in this range, because E is less than V, so P of x prime is an imaginary number. So you can see that pictured here. We have the incoming wave A, e to the ikx, and then the wave decays down to a smaller amplitude, F e to the ikx. And the ratio of F to A is given by this decaying exponential. So the the longer the barrier from 0 to A, the longer A is, the bigger this will be, and the further, the greater the decay will be down to a smaller value here. So we'll get less and less transmitted the wider the barrier is. Similarly, the higher the barrier is, the greater this imaginary number would be, and so the greater the integrand would be, and so we would get the higher this barrier is, the less would be transmitted, the less the ratio of F over A. Okay, and then finally we can find the transmission coefficient, T, which is the square of this ratio, F over F squared over A squared. Just turns out to be writing it as e to the minus 2 times gamma, where gamma is this integral here, the integral 1 over h bar integral 0 to a p of x dx. So that's this integral here. Because we're squaring it, we get e to the minus, this is e to the minus gamma. When we square it, we get e to the minus 2 gamma. So this gives us a really nice expression for the transmission coefficient. Again, even though it's bumpy, if we have this p of x as a function of x, we can integrate it from 0 to a. Even if it's bumpy, we can do a nice approximation to it using a numerical integration or some a method like that. Okay, so that's the Wkb approximation. Again, it's an approximation to solve the time-independent Schrodinger equation, assuming a slowly varying potential, and it gives it's useful for finding bound state energies, and it's useful for finding decaying exponential amplitudes, like we've seen right here. Okay, so that's the Wkb approximation. Hope it makes sense, and thanks for your attention, and I'll see you in class.